Hello and welcome to my model presentation. To begin, let's start out with my big question, and then we can see how it progresses from there. So, I wanted to see what was causing all of the traffic out in front north of Valpo University, and in particular, what solutions can be done to try it. In order to do this, I implemented two possible ideas. One is replacing the roundabout with a stoplight. Due to the unbalanced nature of the traffic, with more of it coming in from the south than going and causing issues with the east-west traffic, it could be faster. Alternatively is finishing the bypass that is already north of Valpo, going by the football fields, connecting it all the way through. So the little patterns that I'm hoping to find inside of that is that these solutions create impact and change the total average travel time for my findings, and B, it's impact in a good way, so they decrease it. Beyond that, I'm expecting and hoping it behaves like regular traffic, where I see stuff like traffic jams, lots of time spent at stoplights maybe, cars packing up. Those would all be signs of organic behavior, which luckily I did find. Spoiler. Okay. Next, let's talk about my data so you can see how we got here. So I chose 5 points, and this is how much traffic what goes through all of them, roughly adjusted from 2018 and normalized to each other. So there was some fun math done between there, which a little suspect at times, but overall I believe it to be accurate. Excuse me. So each one of these is how much time cars go through between those times. So between 0 to 1, aka midnight to 1, you'd expect 75 cars, which isn't a ton going through downtown, but I mean, that's what it turns out it is, so that's what it is, right? Kind of makes sense, about 1 car a minute sounds right for midnight. But then as you get down to 5 o'clock, you start seeing 1,000 cars going through in an hour, and that comes out to quite a few cars if you do the math. Talking multiple cars for every 10 seconds, which that's why it gets so congested, am I right? So I wanted to see, but then I'm like, how do I create these numbers into an actual distribution? And then I remembered Psion distribution allows you to sample time, and you can adjust your sample size. So I was able to change this from an hour to per second, which is my scale. So I was able to get the expected number of cars per second and then sample that as an integer from this distribution, which gives me a theoretically organic distribution that is accurate to this, which I will explain the submodel exactly how it behaves soon. But nothing real complicated with the data. Next, let's move over to the net logo. Okay, so here's my model. You see it sets up. I can choose to have the left bypass and round stoplight on or off, left bypass or the roundabout stoplight. Oh, it's the other way around. Same difference. I was just adding that to that. I forgot to flip a boolean, but you can see I have the 2 choices between there. And this is a pretty busy time right now. This is noon. This is near peak, and you can see the traffic jam is jamming like you'd expect. The stoplight, lots of cars go through. So many are going to the car right now because I dictated that 43% of the cars go to the university. But as we drop it down to maybe a more accurate number, you don't see quite the same surge. Although there's still quite a few cars going to the university just by nature of time of day. Because the university can organically take cars too. So it's just a straight up booster, saying 10% cars extra go here. Particularly I want to draw attention to this, which is the realized speed percent, which in an ideal situation where all cars are going their max speed and it would just be 1, you can see the stoplight obviously has a cyclical effect where cars stop the stoplight, go down, and then it shoots back up. But this overall decrease is a sign of congestion building, which is actually a good sign for the sake of the model, but a bad sign for drivers. Same with it naturally mirrors stop cars inversed. More cars stopped, it's a pretty big penalty. Average travel time, this is a time series with a pretty aggressive alpha over here, meaning that each new input only has about 20% influence on the average there, and you can drag it up all the way to having very little influence. It'll take a long time to get started then. just by nature of how time series works. But eventually it stabilizes. So once it stabilizes, that's a pretty good idea that that's going to be your mean that you can expect. Of course, it will never be exactly stable, but within the vicinity. And that's one really powerful way to measure how effective these are, as well as your realized speed percent. Total supply and demand, you can see how they invert each other, but not precisely. I can select this and just make it bigger for the sake of viewing. Demand is basically how often these points want a car, and if demand gets too high, up to 5, university will start spawning cars, because there's no data coming through the university. Besides that, I want to make sure I don't miss any of these points. I'm just going to double check the sheet. Okay, let's go through the variables. We start with the globals. This is the direct imported data that you see from my spreadsheet, which I just shove inside this thing called traffic data for the sake of easier. Time of day, weather condition, transform factor, these are all just settings that help determine how far a car can see, how many cars come through. And this is just for me changing the scale when I was doing some bug testing, because I had issues where cars wouldn't quite go in the same line because of rounding. Yes, you're technically headed to the same point, but that point is such a wide box that it ended up getting messy. Okie dokie. Next up, we have our breeds, which are cars and controllers. Breeds are, of course, a way to separate our agents. I did everything with agents. I could have used patches for stuff such as the stoplights, these points, or any of the other sort of things. Like there's speed signs that aren't currently active, but they can be implemented if you wanted to test one as an alternative solution. Such as raising the speed limit in a certain part of the road. But those are known as controllers. I chose not to use a patch just because I liked how the agents looked better. That's the honest truth of it. I think having these icons that change color and are separate, or like a target and a star, just looks prettier. And I thought that was worth it. I could have, of course, made something like had the stoplight be red and green. Back to focus though. So basically everything is done with breeds, nothing is done using raw totals. We have these links, which are only used to handle stop signs connecting with traffic. That way they can determine who they've already stopped and who's free to go through them. So it creates a link, and then that link is replaced with a link that says I've already stopped at you. Points own, this is the data, if they have one. If they don't have data, such as the university, we give them a vector of 0s to say they never demand and never supply, and so they only absorb or are used for routing. And their name, this is like the primary key if you take in data bases or whatever. Basically, when I need to grab a certain point, I just use this name to find it. It works, right? And then controllers, pretty simple. What type of controller is it? Does it have a speed limit? If it's like, is it a sign? Or then is it active? Because you can always deactivate them. So we set up, we make our entire thing green, we reset. This is transform factor, it's just used because I'm currently using 80 by 80 instead of a 16 by 16. So this just applies a linear transform and stuff like how far the cars can view, the location of the points, the speed. Maybe I'm missing something, but so we'll encounter it. This is just used as a placeholder default. Time of day, we default to 5 AM, but of course, it takes precedence over that. So it's just in case something bad would happen. Weather condition, we default to 0 2. This can be modified through stuff like experiments, but I didn't find a lot of value in it, so it's kind of tossed away right now. We start the stoplights out at green, and this is just a global variable used for all the stoplights. They change in synchronous with each other based on whatever is defined on this main page. And just to be clear, none of these are changed during the model run itself. These are all things that are set up. The only variables that change are ones internal to the cars, being their speed, their links, and where they're going. And based on how they behave is where we get all of our descriptive statistics. This is just, I'm not going to walk through creating all of these, but just for example, we create a stoplight, we transform its size to make it look good, and we transform its location. This way it always appears correct. This will probably break some stuff, but just as a demonstration, you know, because you'd also have to change all of the size. You know, what is 96, apply, set up, go. And in theory, it still works. Of course, some stuff breaks, but this was really useful for beta testing. I just like showing it off because I made that and I was having some real issues without it. Okay, back to 80 for you. That's what happens if you mess up your math, things break. Okido. Hope they don't get too long. Okido. Where was I? Yeah, so all of these are the same. Load the traffic data if it's 0. If it isn't, we just load the data from the file, which is already loaded earlier inside our local traffic data. It set its default supply demand to 0, give it a name, and just plop it on the map. And this is what's actually used to load them. I mean, it just reads the file. Hopefully you've all done it by now. There's really nothing fancy going on here. It's just kind of bulk doing it. They're actually stored in 5 separate files, but I just put them all in one for the sake of my viewing and understanding. But I don't want to open up 5 files just for you guys. So here's the main lifeblood of this model. Here's our loop design. Cleanup is just used in case anything goes crazy. It just checks for some outliers and purges them. It's not ideal, but things do sometimes break, and this just keeps the model clean and running. So we start out by updating demand. Let's jump to that declaration down here. This is one of the parts of the model, is where we update our supply and demand. We'd sample our sign distribution by a half of what you'd expect. This is just based off the university rate being the amount the less that we want, that's automatically driven to the university. So if you can think about it this way, that if demand is lower on the other points, the extra supply has to bleed off somewhere, and it chooses to bleed off to the university. So this way we can actually directly influence how many cars go to the university without manually adding or subtracting, so we attempt to preserve our ratios that way. It does have some consequences, but we address that through bleeding off extra supply, because by this nature we do generate a bit less demand than we do supply, although they should be, in theory, be equal. So when we get significant demand under supply, we bleed it off through spawning cars at the university level. Besides that, you can just use 60 divided by 60 to get to seconds divided by 2, because half of it should be going to demand. It's going through, half goes to supply. Okie doke. Next we arrive. Arrive is really simple. Arrive. Did I not do that? Am I done? Or am I just blind? Arrive control. There we go. Okay. So we basically check the car and any points behind them, because sometimes at higher resolutions the car will actually drive over the points. We check the patches behind as well, and if that patch is found, we update their heading to go to the new patch, and if it's their final one, we add their travel time to the running time series exponential average of this and kill the car off, because it's arrived and it's no longer needed. So we don't store data about already arrived cars beyond how long they took, just for the sake of keeping important metrics. Update stoplight. Also pretty simple. We have a 313x cycle there. So it goes for basically however long you put this on the green and red. We can just break it down. It stays there. Boom. Simple enough. You can see the code right here. And it works. Yay. Basically, if it's less than 3 and it's yellow, we move on. Otherwise, we check those two if it's greater than stoplight. Nothing real fancy, but that just keeps all the stoplights synchronized together. Satisfy demand. This is maybe the most complicated of the submodels. You could argue it should be multiple, but I felt keeping it as one made sense. It kind of works with the same way as generate demand. So we check if there's any supply in a point, and if there is supply in a point, we look for other points and see if they have any demand. And if so, we recognize that supply can meet the demand and spawn a car through that route. and that car will also be going through other points, and as they go through, we satisfy the demand of that point. It does have some delay to it, but overall it functions pretty well to create a healthy environment. And this one is basically bleeds off. If there's no supply and there is demand, we give the university a chance of spawning a car and then just killing off the extra demand. This basically satisfies too much demand. It tries not to do it all at once because then you get a ton of cars on top of each other, which doesn't seem very ideal for distribution. Admittedly, this is a bit of a heavy-handed way of doing it, but it functions and it stops the university from always just spawning clumps of cars, instead spaces them out some, although it still can duplicate, so it's the closest as I can get to a random sign distribution through there. And then if there's extra, we just totally just bleed it off. So yeah, total demand, this is just a reporter, but we'll get back to that later. Okay, limit speed. So we check every car. The way that we handle speed in this model is at the start of every round, we assume a car is going as fast as possible, which is of course their maximum speed. And then we check if they're next to any stop sign, speed limit, and if so, we lower their speed. And then we check if they're next to any, like inside a stopping link with a stop sign, and if there are so, we of course stop their speed because they're stopped at a stop sign. Additionally, we'll check if there obey stoplights, if they're in the area of any stoplight that's red and going the correct direction. We ask the car to obey stoplight. Very, very fun. Thank you. There we go. As the note here basically says, we look at the ahead patch, and if there isn't a head patch and there's a controller on that ahead patch, if it's a stoplight and the polarity of the stoplight matches the direction, so we just assume that all the stoplights are north-south and east-west based, and it creates a pretty good approximation, and we determine if it's going more east or more west via is vertical, and if it's the wrong color, of course we stop it. This is how we get that behavior where you see V stop and then university doesn't, and vice versa, just because these are going vertical so they can bypass, but they can't go through a green, but they can bypass red. Okie dokie. And that of course is just done through checking the heading. It's pretty ugly, but I mean if it works, right? Check if it's inside one of the two headings that are up and down, report true, otherwise it's not. So it's false. Science. Ready to go. Release stop, this uses our timed links. So we ask all of our normal links. Basically, if it's been created for longer than 6 seconds, this can of course be adjusted down to whatever. Usually I keep it at 4, but I find it doesn't have too big of an impact when I did my analysis of that. It really just kind of adds on some time to it all. It's not insignificant, but it grows pretty linearly with the numbers, so I don't like playing around with it too much because I'm just manually editing the final results in a non-organic manner. So if it's been created for long enough, we create a stop link, which basically tells that this stop link means a stop sign link that's already been used up all the way, and we set it to hidden so it doesn't show up on the screen. Then we give it 2 seconds of immunity, just from other things that could tell it to stop. In case it might see a car or a car glitched inside of it, we can get some pile-ups, which doesn't usually happen, but I just like to catch in the edge cases because they sort themselves out within 2 seconds always. And then we give it stop wait time of 0. Basically, get going. And then we kill off the link because this link tells any car that's in a stop link, a normal link, automatically gets stopped, as you remember from earlier. Oops, I've used control find so much that I don't even remember my own codes anymore. And check for links. Super simple submodel. We basically check to see if there's any stop sign that's not in a link with in the area and doesn't have a bypass link to. If so, it creates a link, and that's pretty much all of it. Yep, create a link, summon it, boom. And the parts that I haven't gone through. Let's just make sure I've covered all the code. Yes, 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 yes. Check path. Basically, yeah, this checks if there's any car in front of it that's not moving, and if so, we set its speed to the minimum of it or 95% of the cars in front of its speed. This creates a really nice acceleration effect that models reality. Basically, you can't go faster than the car in front of you is all it's saying, which makes sense and tends to be pretty accurate in my experience with driving. If you are, you tend to hit them, which not the best thing. Okie dokie. This is just a really brute force way of generating, like I said, waypoints. I call a waypoint each one of these points that it has to get routed through. So we basically start off, we build the route based on where it's starting and where it's ending, and it's straight up a branching tree that branches from the start point to the end point and has a pre-made route. This way works. It's yucky, but it works. And then it has multiple modes for if left bypass is on, because if not, it has to route up through left. If it doesn't, it goes through left bypass when going the route that obviously benefits from it, aka not going through one of these. Yeah. And then it just, of course, sets the car. Okay. Our reporters are pretty simple. We sum the speed of the cars by the target speed of cars, and speed will never be more than target speed, because at the start all the speeds are set to the target speed and they can never increase from there. It's this way that we can always get the percentage speed. Sometimes like a rounding error happens and it shows a little bit higher, but in practice it's never. And then just when graphing, you get like 100%, it gets sometimes a little fuzzy-wuzzy there on the graph. But stop cars, also really simple. Count how many are stops, divided by count. And then finally we have our surge. This way just basically summons cars at the university, you know? And it creates kind of a backup traffic jam there, which not great for the university, but it does help explain why some of these backups might happen and these traffics, and it does basically crash the relay speed percentage for a while. Yeah, okay. I'm going to pull up the spreadsheet and make sure I covered everything. I would hate to miss out on telling y'all something. Okay, so sequence of the model, I believe you've seen, and they do populate with the correct variables, and I have tested them at their importance. They basically execute in the order of my to-go loop. Basically this. I think it's pretty clear. Oh yeah, and just to explain the check path multiple times. Basically, cars, it executes in a random order, and sometimes you can roll bad orders that might not see the car in front of you stopping at a stop sign. So we just kind of brute force it 3 times and it works. It feels silly, but the odds of a car getting through it are really low. You could, of course, run it multiple times, then check the total speed. But I found that was actually just taking longer to run, so I figured this way works better. It's kind of just a gambling game, and then just ask all the cars finally to drive forward their expected distance, which this creates a really nice, simple way to manage the cars. So basically we process their speed and then drive. Sounds silly, but hey, it works, you know? And then all of these are static during runtime. The only dynamics are in the car. The entities, of course, are just the cars, the points, and the controllers. And I do believe I need them all to answer the big question, as these kind of are the primary elements of driving, where you're going, your car, and traffic elements. Adding anything, missing any of these 3 would be pretty detrimental to the ability to model. Frankly, I'm using a lot of the design concepts from the list. Emergence is a very important one, because I'm seeing the emergence of traffic behavior and complex stopping. When it goes, like the traffic jams, like you see, you can see multiple cars take time to go through each stoplight, which is not, of course, a pre-programmed behavior, only if they stop. But you can see they end up waiting multiple stoplights as they creep forward in advance, as well as cars packing up, which is especially apparent at lower densities of cars, such as in the morning, which Just for example, you can see that, as expected, there are not many cars driving out at 3 a.m. And then, of course, we can also see this all in my info, just so I don't miss anything out. But what we're really measuring here is a higher level interaction between the cars. On an individual level, it's not really important what a single car does. It's only important what they all do together and how they interact. So emergence is really important. Sensing is also being used. I just want to make sure that's one of them before we talk about it too much. Yeah, sensing. All the cars basically have to sense the environment around them, but also the cars in front of them and react to it. If the car couldn't tell how fast the car in front of it was going, it wouldn't know to stop, and you'd have cars on top of each other and cars not routing correctly, which would prove really problematic. You've seen my stochasticity. You've seen my collectives. I don't know, I'll talk about the stochasticity. Every single run is different just because it's sampling from the sign distribution. And that, of course, the whole model is driven by randomly generated traffic patterns. You'll never get the same round twice. So it's a super important idea of the model, which allows for a lot of reproducibility in its usage. Let's see. Just in case, let's do one more. I mean, collectives, like you said, like you might saw, I use the cars as a collective to model different agents, as opposed to that other way. Although I've also a form, I used trucks at one point as well as cars, but due to trucks only existing for about 2% of the traffic and behaving relatively similarly, I decided not to go forward with using them. Yeah, I think that's 3 at least I've talked about, and hopefully is clear. But as always, if you want to read any more, my odd is here, and we'll cover that just for you. Interaction, prediction, and sensing. The goal of being optimization is the final end goal. When I initialize the model, I basically create points based off of where they are on the map, which I basically just mapped out on a separate photo and then manually figured out where the points should be based off that. I'm using site-specific data just for, well, gathering the points, of course, and the specific different simulation scenarios are dependent by the time, which, as you can see, is important. You can also adjust the time live. I just choose not to because it kind of just confuses the data when you have a bunch of cars spawning and they stop spawning and you're like, this is kind of weird, because time doesn't tend to do this in real life. But you can if you really want to. Okie dokie. And yes, I think submodels are executing as planned. They have been tested, and I have played around with all of them. And generally, they're all really structurally sound. I do confess the sign distribution does have some issues at times, and I'm not 100% with how it works, but I do believe it is the best choice out of a series of bad options for generating random traffic flow when done through a series of points without any sort of directionality. If I had ideas of how many were going left or right at each point, I could make much better estimates and create a more accurate model. But as it is, I'm just having to make guesstimates and assuming that half are going through each direction, which is, of course, logically probably not true and would adjust during the day, but I have no current way of knowing this information. My interface screen basically describes the key metrics that I use. Stopped cars, possibly good, possibly bad, but really they're important in relationship with the relay speed percent. This is the premier thing, as well as average travel time. These two will strongly reflect each other in theory. In practice, the alpha of this is so high that it tends to rather stabilize out, or relay speed percent, which is not bound to any of that, will follow the fluctuations, but its general trend shows the same general trend as this, as well as this is just not super important for understanding the big question, but it is really important for understanding how and why the model is functioning as it is. But yes, I do believe, especially once this alpha is way too, you can see, just give us some extra gas, that you can really identify if your thing is working or not based off your statistics that you measure here. Okie dokie. What next? In terms of sensitivity analysis, I can show you what I've done in R. Hopefully my experiment is built into this model. I know I've saved a couple extra ones, so yeah, this is my sensitivity test. I just tested all of these. This took 30 minutes to run, so I'm not going to run it again tonight and do the full analysis, but I can show you what I got out of it. Is I ran 650 ticks for all of these, just because my alpha wasn't set to super high, but you could be more aggressive, but I wanted a more consistent and a really high alpha makes it so that basically using the mean value of the last ones in practice after it gets consistent, which I liked, and I ran it all at 12 o'clock. In terms of sensitivity, I didn't want to test this one out because it's going to be extremely influential, possibly so much so that it ends up dwarfing some of the other ones by absorbing some of that and creating different behavior, because of course there'd be interaction effects between what a stoplight might do, what an extra routing might do at 2 a.m. versus 14 a.m. just based off total traffic flow, which I wasn't interested in the model telling me that cars can go faster and nobody else is on the road, because hopefully we all know that one. It does work, by the way, in this model. In terms of this, let's get that pulled up. There you go, OBS quick. And bring back everyone's favorite software, R. So this is where I did my sensitivity test. The model is actually pretty well set up to handle this, because you can just run simulations, grab the average time, and use that as a Y value to really model the entire effects of the model. You can see that the model has been basically tuned, by the way, to run at 148 seconds or 150. It's just based off, that's how long it takes to drive there. So it isn't entirely functional just based off distance, but rather this way, it is to have a linear relationship with the real world, but there is no exact conversion factor that I found or done the math for, although you could if you wanted to. So I run independent regressions for all of these. Basically what it comes out to being is that adding more stoplight time makes the model take longer by about that much, which is frankly about what you'd expect if each car stops once or twice. You get roughly that much. It's a bit more than a 1-to-1, but it's close, I believe. It's self-memory, but yeah. Pretty much. And then the university rate, which unsurprisingly, it's not super great. 0.22, and then the university rate comes in, so at 100 at max it's 22 seconds. Basically what this is just saying is that even if every car is going to the university, which is kind of silly, it ends up shaving off time, but it also isn't a great way to measure time, because the different distances being traveled is of course different. You know, if a car has to go from Greenwich to LaPorte, it of course is shorter than Greenwich to university. So this rate is really more useful in the context of just measuring bigger events with surges and whatnot, or to find an accurate tuning. The big influence too is when I tested the left bypass, it ends up shaving off about 7 seconds, and it bypasses the stoplight and takes you straight to Greenwich, which is really influential because not all the traffic is being routed through there, so they're really saving time by bypassing that stoplight, both these stoplights, which is one major benefit. Okie dokie. Beyond that, I also did, that's all I did in the sensitivity analysis. You can of course do the exact same thing with turning on the roundabout stoplight, or in this case, as well as just adding a surge in. You can say add a surge and then run it after 50 ticks or so, and this way you can get an idea of what it looks like when the university is dealing with. You can see that the surge is really struggling, but yeah. It gets upset because the university has cars constantly coming in, so it doesn't like to spawn then. But yeah, that's the idea. What I plan to do with this model is to run experiments based off enabling different solutions with slightly different stoplight times to try and see if I can come up with a proposal that results in an optimal solution that reduces traffic congestion, stops cars, without having too much additional financial demand. Because of course you can always say, what if you just build 1 billion roads connecting all the points? And you're right, that would be the fastest, but that is not a practical solution. Beyond that, thank you for your time, and thank you for listening to me rant for half an hour. Bye. Hi, it's me again. I noticed a couple things. First, I was on the R for the entire last part of that presentation, which wasn't entirely useful for you guys, but it's only a couple minutes, so I'm definitely not recording that whole thing. And second is I forgot to show you Extrema. I did a little bit, but just to show what it teaches about the model, I want to go through this now. So it shows, first of all, let's do stoplight time very little, as well as everything going to university. It shows the model is relatively robust to relatively strange conditions, as well as pretty much just that. I found the model has been robust to pretty much every single condition I've thrown at it. In particular, this is the peak of traffic as opposed to very low traffic around here, although please turn my eyes. So I can set my very low condition, and this can be my very high condition. I'll talk about it. This model just demonstrates how traffic jams form. It's going a bit fast just to demonstrate, but you can really see how they all bunch up. They slowly slide to consolidate, much like you might see in regular traffic, which I'm happy with. Just disable the left bypass quick. Just so you can really see the traffic build up. You see it builds all the way back up to the left. It does teach us that the model is pretty good about traffic, although it is of course not perfect. But overall, I haven't found any real extrema conditions that really break the model in ways that are just completely unexplainable. Like you see, I can search 200 cars with the model, and this will have some issues, but overall the model can handle it. I mean, there's not a ton of, in terms of understanding what my problem to be understood, besides the fact that when you surge a lot of cars to the university, you can see a spike, which is good. That is the behavior we expected, as well as you have to account for those additional cars, how long they took to get on the road, which, strictly speaking, I don't have a way of accounting for right now. And then that's pretty much all that. What else did I talk about after R? I just kind of showed off the surge, which you saw right there, how it spawns all the cars and goes, as well as university rate and showing the time, how little it is at midnight. This would be like the least extreme version of my model possible. Which just goes to show that stuff works, basically. And yeah, you can see the supply and demand. Demand tends to outpace supply, just based off the fact university rate existing, but that is totally okay. It's what expected. Yeah, I just want to make sure I have everything. Pulling up Canvas again quick. And I do realize that technically you could consider that these are all mean values inside my model, but I consider them to be the extrema, just because really what the model is being based upon is throwing in 24 different sets of data and seeing 24 different models in one that just follow exact same behavior, modeling 1 p.m. behavior, 2 p.m., 3 p.m., etc. So yeah. Let's make sure I have this. I've explained that. And yeah. So each output basically just tells me that the model is stable. It does struggle with handling the traffic that backs up longer than just one row. I haven't found a great way to fix it because when it detects, it looks forward, and it doesn't know to look forward and then this way. So you do have that issue when people park in the middle of the stoplight, but then again, that also happens in real life. So I guess we can call that intentional behavior. Yeah, sweet. Sorry for showing you the R screen the last 5 minutes or whatever there. Bye.